Welcome to Chapter 3 of the Basic Chemistry series. First, I want to go over what we already know from Chapter 2. We know that in the center of an atom, there is a proton and there is a neutron. Together, this is called a nucleus. And the electron is in the outer part of the atom that orbits the nucleus in different energy shells. We know that the periodic table is set up in rows that go horizontal, and these describe different shells. So the first row would be period 1, it would have 1 shell. Period 2 would have 2 shells, and period 3 would have 3 shells. We know that the groups or the vertical columns describe how many valence electrons are in the outermost shell. So looking at group 1, as we go down the periods, period 1 there's 1, in column 1 there would be 1 valence electron on the outermost shell. For column 2, this column, period 2 there's 2 shells, and period 3 there's 3 shells. So this would mean there are 2 valence electrons in the outermost shell. We know that an electron is built to the electron configuration through orbitals. From the Aufbau principle, we know that we start with the lowest energy value, which would be 1s. 1 electron would be hydrogen. If we wanted to go to helium, we would put 2 electrons in an orbital, which would be this box. We know that only 2 electrons can be in an orbital, and they have to be of opposite spin. So we describe that by putting arrows, or 1 arrow is pointing up and 1 arrow is pointing down. If we wanted to go to lithium, start another orbital, which would be 2s. If we wanted to go to oxygen, we'd start the 2p orbital, which are all of equal energy. Then we would fill in orbitals of equal energy, the same spin first. Then we would come back and start filling in orbitals with opposite spins. In addition to what we learned in Chapter 2, before we started in Chapter 3, I want to point out a category on the periodic table that is called the main group elements, and that involves the first and second column, or 1a and 2a. And then I want to go over to column 13 or 3a through column 18 or 8a. And these are called the main group elements. So up to this point, we've talked about the atom, the different subatomic particles of the atom, and how the atom is constructed. In this chapter, I want to go into how 2 or more atoms are brought together and how compounds and molecules are constructed. The atoms and compounds are held together by attractive forces called chemical bonds. There are 2 main types of chemical bonds, ionic and covalent. Ionic bonds do not share electrons, but form bonds through electrostatic attraction of positive and negative ions. Covalent bonds do indeed share electrons. To understand ionic bonds, we need to know why atoms form ions. The best way to describe this is through what is called the octet rule. In 1916, Gilbert Lewis pointed out the lack of reactivity in the noble gases of group 8a, indicating a high degree of stability in their electron configuration. Helium, with its filled valence electrons of 2 electrons, 1s2, which would be right here in group 8a. You can see, going back to the electron configuration, this would be 1s, it has 2 electrons in the orbital. Neon, with a filled valence shell of 8 electrons, and it has a filled valence electron shell of 8 electrons right here. And argon with a valence shell of 8 electrons, 3s2 and 3p6, and so forth as we go down the group. So in this column right here, all the valence electrons are filled. Very quickly, I want to go over some characteristics of the noble gas group, or the column 8A, with some things that we already know. We had mentioned that period 1 has 1 shell, period 2 has 2 shells, period 3 has 3 shells. And using the Bohr model, we'll start with helium. It only has 1 shell, so it would have 2 valence electrons. So this is completely filled, and we can find that with the electron configuration and the box arrows right here. We can see the electron configuration right here. Moving down to neon. Neon would be in the second period, so it would have 2 shells, and it has a filled valence shell. This has 8 valence electrons. There's 8 electrons in this outer shell, which would be filled. And looking at argon right here, this is the third period, so it would have 3 shells. So in the outermost valence electron orbit would be this ring or orbit. And essentially what the Lewis dot structure is doing is, instead of writing all this down or all this down, we just simply write the element abbreviation, like for argon, and there are 8 valence electrons. Because it's in column 8, it would be 8A. We just put 8 dots around it, and it's done. So let's get back to the periodic table. Pay attention to the A groups. We have 1A, 2A, so on. Notice that this portion of the periodic table is labeled with column B. We will not use this for what we were talking about. What we want to pay attention to is the main group elements, which would be this area and this area. So if we took periodic table and collapsed it down to the main group elements, we would have something that looked like this, where it had 1A through 8A. And we can see how the Lewis dot makes very quick work of what we just went over. Hydrogen would have 1 valence electron, helium has 2 valence electrons, neon and argon have 8 valence electrons because they're all in groups 1A. Groups 2A has 2 valence electrons, 3A has 3 valence electrons, 4A, and so on. So to wrap this up, we know that valence shells are the outermost incomplete shell. A valence electron is an electron in the valence shell. The symbol of an element represents a filled shell or filled shells. The number of valence electrons is the same number as the group number. Before we get into the nuts and bolts about the octet rule, I wanted to define what an ion is. Before we've seen, as we go across the periodic table, the number of protons and electrons are added equally. Hydrogen would have 1 proton and 1 electron, helium would have 2 protons and 2 electrons, lithium would have 3 protons and 3 electrons, and so forth. When an ion is formed, this is no longer the case, and there's an unequal number of protons and electrons. Atoms and their ions are nothing alike chemically or physically, making them entirely different species. Here we have a lithium atom with 3 electrons and 3 protons, and here we have a lithium ion with 2 electrons and 3 protons. So the protons and electrons would not be the same or not equal. Here's a fluorine atom with 7 protons and 7 electrons, and this would be a fluoride ion with 7 protons and 8 electrons. So the protons and electrons would not have the same number of subatomic particles. So the number of protons and electrons would no longer be at a 1-to-1 ratio. The octet rule says there's a tendency for elements in groups 1A through 7A to react in such a way that achieves an electron configuration of 8 valence electrons. So looking at 1A, and we went down to lithium, and group 7A, we have fluorine. The best way for lithium to reach a full valence electron configuration where the outer shell is filled would be to lose an electron, and fluorine would assume a filled valence electron configuration of 8 valence electrons by gaining an electron. A metal atom that loses 1 or more electrons becomes a positively charged ion called a cation. A nonmetal atom that gains 1 or more electrons to become a negatively charged ion is called an anion. I want to take our table and break it up to illustrate an idea of what is happening. Looking at the lithium would have 2 shells, and it has 1 valence electron on the outermost shell. so it would lose an electron to reach the noble gas configuration of helium, and fluorine gain an electron to reach the noble gas configuration of neon. So metals will lose electrons to become cations, and nonmetals will gain electrons to become anions. Here's a more detailed table just for completeness sake to illustrate what ions would be formed. So going down to the third row, we would have sodium. It would form a charge of 1. Magnesium would form a charge of 2. And in the third column, aluminum would form a charge of 3. Moving over to the nonmetals, fluorine would form a charge of -1. Oxygen would form a charge of -2. And nitrogen would form a charge of -3. Let's take a look at what's going on here. If we pick group 1A and we select sodium, sodium has 11 positively charged protons and 11 negatively charged electrons to give a net charge of 0. Writing the electron configuration, we could write, or we could write the Lewis dots. So the sodium ion is then wrote as, it still has the same amount of protons, which would be 11. Metals lose electrons, so it would now have 10, and that would give us a charge of 1 and give us an electron configuration of this. So moving over to the nonmetals, we could choose group 7A, say chlorine, and chlorine has 17 protons and 17 electrons to give it a net charge of 0, and the electron configuration would look like this. Drawn a Lewis dot structure, would have a outer valence electron shell just shy of a full octet. Chlorine atom would then gain an electron to bring it into a full octet of the noble gas. So that would give us a total of 18 electrons. So the electrons would equal 18 and the protons would equal 17, leaving us a charge of -1. So chlorine would have a charge of -1 and sodium would have a charge of 1. At this point, I would like to illustrate how an ionic bond is formed. So we have a metal and a nonmetal. We know that metals lose electrons to form a cation, and nonmetals gain electrons to form an anion. So you can kind of guess what happens here. The one valence electron on the metal goes to the nonmetal, and we have the metal cation and the nonmetal anion with the 8 electrons in the valence shell. And through this, there's an electrostatic attraction. One thing I do want to point out is there is no sharing between an ionic bond. It's a complete transfer of the electron from the orbital of the metal to the orbital of the nonmetal. When writing formulas for ionic compounds, the total number of positive charges must equal the number of negative charges. And so far, we had sodium chloride, which is a 1-to-1 ratio. But obviously, all ionic compounds aren't 1-to-1 ratios. So let's split this down the center. And if we wanted to go to group 3, where it has a cation of 3, just put 3 here. And we went to group 7, where it has an anion of 1. This has to match somehow. And we can do that by adding 2 more ionic species to where it finally balances out. So we would have 3 different ionic species of -1 to total 3. A quick and dirty way of doing this when writing ionic formulas is the crisscross method. So for example, if we had barium, which has a positive charge of 2, and iodide, which has a -1 charge, we would just crisscross these like this and rewrite the compound like this. The subscripts represent the number of atoms in the compound. So iodine had a negative charge of 1, so it would come down to barium. We could put 1 there. Barium had a positive charge of 2, so we could put 2 on the iodine. And by convention, if subscript is 1, we just leave it out. So we could just write barium iodide as the formula. Another example would be if we went to the third group with aluminum, where it has a positive charge of 3, and we went to the sixth group with a sulfide ion with a negative charge of 2, we could simply crisscross the charges. So it would be aluminum, then put 2, and then S for sulfur, put the positive charge of 3 on the aluminum as a subscript on sulfur, subscript of 3. And this would then give us aluminum sulfide. And these are what is called monoatomic. When there's ions of more than one atom, it's called a polyatomic. Poly meaning more than one, mono meaning one. So let's look at some polyatomic ionic compounds. So we have the sodium ion and the bicarbonate ion, and these are a 1-to-1 ratio, cancel out very nicely. So it would just be written like this. And I'll show you a polyatomic ion that is not a 1-to-1 ratio, just to show you how the crisscross method would work with that too. One is potassium, the positive charge, and the phosphate ion that has a -3 charge. And then we would just crisscross the charges. So that would become K3PO4, which is potassium phosphate. I want to briefly go over naming ionic substances. For the main group elements, the naming system is pretty straightforward. Elements in groups 1A, 2A, and 3A form only one type of cation. The name of the cation is just the name of the metal followed by the word ion. So with hydrogen, it would just be hydrogen ion. Lithium, it would be lithium ion, and so on going down. For group 2, it would be the same thing, magnesium ion, calcium ion, and for aluminum, it would be aluminum ion. The ions can only form one charge, so the naming system does not need to be complex. Next, we can start naming monoatomic anions. Anions are named by adding IDE to the stem of the name. Here's some monoatomic anions we deal with most often. So looking at nitrogen with a negative charge of 3, we would put IDE after the stem, so it would be nitride. And picking one from group 6, oxygen has a negative charge of 2. Stem is ox, so we would put IDE after the stem, it would be oxide. Looking at group 7, stem name would be fluor, and the anion name would be fluoride by adding IDE to the stem name. So far we've named monoatomic ions. Now we can move to polyatomic ions. I can show a few tips on naming these, but the best way to learn them is just to memorize them. Starting out with ite and 8 with nitride and nitrate, you can see that 8 has one more oxygen than ite. Something else to point out is the prefix di. There should be a 2 on this, and di means 2. Here we have dihydrogen. That means when it's a prefix like this, it means there's 2. So there's 2 hydrogens on dihydrogen phosphate. Again, with sulfur, there's ite and 8. 8 means there's one more oxygen. Now let's talk about binary ionic compounds and how to name them. Binary ionic compounds contain only 2 elements, and both elements are present as ions. To name the ionic compound, we first name the metal that the cation was formed from. So an example would be sodium chloride. The sodium ion came from the metal sodium, so the first part of the name would be sodium. The second part of the naming system would be to simply name the anion. So in sodium chloride, the anion would be chloride, so the name would be sodium chloride. So I'm just going to make a table and give some examples of names. So we have the metal of the cation plus the anion. Examples would be lithium bromide, silver sulfide, sodium bromide, magnesium chloride, aluminum oxide, lithium iodide. So again, these are the metals that the cations were formed from on the left, and these are the anions on the right. A couple names I want to highlight or point out is aluminum oxide and silver sulfide. If you notice, their formulas have a subscript. The silver has a subscript of 2 right here. Aluminum has a subscript of 2 here, and oxygen has a subscript of 3. We do not take this into consideration when we name the compound. These are simply negated. Next, we can look at ionic compounds that have polyatomic ions. To name ionic compounds with polyatomic ions, we first name the positive ion and then we name the negative ion. When we name the positive ion, we name the metal that the ion was formed from, and then we name the negative ion. We've already went over naming polyatomic ions, so with that information, we have everything we need to name this ionic compound. We can split this up and find that the positive ion comes from the sodium atom, so the first part of the name would be sodium. We can find the negative ion right here, and we know how to do this from naming polyatomic ions. And from that, we know that this is nitrate because there are 3 oxygens. We can break this up into 2 parts as well. The positive ion would come from the metal calcium, so we write calcium. The negative ion is carbonate. Going below this, we can break this up into 2 parts. The sodium ion comes from the metal sodium. The negative ion comes from dihydrogen phosphate. Now we can move on to covalent bonds. Before we do this, I want to go over some things that we already know about bonding and ionic bonds. Using the Lewis model, atoms bond together in such a way that each atom acquires a valence shell electron configuration of the noble gas of 8 electrons. We know there's 2 main types of bonds, ionic and covalent. We know that ionic bonds form bonds between atoms with the loss or gain of electrons to acquire the electron configuration of the noble gases. So sodium loses an electron and chlorine gains an electron to reach the noble gas with 8 valence electrons. Sodium has 1 valence electron and chlorine has 7 valence electron. Sodium loses an electron, chlorine gains an electron to give a compound with a bond where sodium has an electron valence configuration of neon and chlorine assumes a valence electron configuration of argon. They do not share electrons, but there is a bond between the 2 atoms that is an electrostatic bond, where the 2 atoms are held together by the attraction between the negative and positive charges. So the ionic bond would look like this, where no electrons are shared, but there is an electrostatic attraction. Let's move on to covalent bonds. Covalent bonds share electrons to assume the electron configuration of the noble gas. A good way to describe a covalent bond between 2 atoms is with the simplest atoms, hydrogen. Here we have hydrogen with 1 valence electron on each atom, and when a covalent bond occurs, the valence electrons are shared. So looking at the periodic table, we have 2 hydrogen atoms, which is right here. So when there's a bond between 2 hydrogens, and the electrons are shared, the electron configuration reaches the noble gas state of helium. Let's look at some more diatomic molecules that are covalently bonded. Here we have nitrogen, which is right here on the periodic table. And nitrogen is in group 5A, so it has 5 valence electrons. So in order to reach an octet, it would have to gain 3 valence electrons. So this is done by sharing 3 valence electrons with another nitrogen, and together they make 3 bonds to reach the noble gas of neon, which would have 8 valence electrons. Here you can see that the diatomic molecule shares 6 electrons, and each atom shares the 6 electrons. So this atom shares 6 electrons, and this atom shares 6 electrons, which would give it a full octet. Let's take a look at another diatomic molecule that's covalently bonded, which is diatomic fluorine. The element would be found right here on the periodic table, and fluorine is in group 7A. So to reach the noble gas configuration of a complete octet, it would have to gain 1 electron. So fluorine right here needs to gain 1 electron to get to the noble gas configuration of neon. And you can see the fluorine has 1, 2, 3, 4, 5, 6, 7. And with covalent bonds, all the bonds that are shared count towards getting to the noble gas. So this fluorine would count all of these electrons that are shared, giving it a full octet. So it would have 1, 2, 3, 4, 5, 6, 7, 8 valence electrons. And this fluorine atom would do the same thing. It would count both electrons that are shared, 1, 2, 3, 4, 5, 6, 7, 8, to give it the electron configuration of the noble gas. Where ionic bonds, like sodium chloride, will not share an electron, but an electron is completely transferred from one orbit to another, from the sodium atom to the chlorine atom, for each atom to gain an electron configuration of the noble gas. So far we've described ionic bonds and covalent bonds, but we've described this through a subatomic lens. To give a more quick and general way to determine whether or not a molecule has bonds that are ionic or covalent is by looking at the periodic table. On the left side we have metals, and on the right side we have nonmetals. This black diagonal line separates the metals from the nonmetals, and these elements along each side of the diagonal line are what are called metalloids. And a quick and general way to determine whether or not a bond is ionic or covalent is by determining whether an atom is a metal or a nonmetal. So metals bonded with nonmetals will generally have an ionic bond, and nonmetals bonded with the nonmetals or metalloids will generally form covalent bonds. Covalent bonds share electrons. Sometimes they are shared equally, sometimes they are not shared equally. To explain why they may or may not be shared equally, we need to understand electronegativity. Electronegativity is an atom's ability to compete for electrons with another atom. This is a periodic property that depends on the nuclear charge and the distance of valence electrons from the nucleus. This can be explained in 2 ways. The number of energy shells between valence electrons in the nucleus, and Coulomb's law. We have somewhat of a good idea of what the shells of an atom are, so let's look at Coulomb's law. Coulomb's law says the magnitude of the attractive or repulsive electrostatic forces between 2 point charges is directly proportional to the product of the magnitude of the charges. And that would be this portion of the equation, and inversely proportional to the square root of the distance of them, which would be this portion of the equation. This is a very fancy way to say when 2 point charges increase, the electrostatic force will increase, and when the distance between the 2 charges increases, the electrostatic force will decrease. This is very intuitive when you think about a magnet. The bigger the magnet is, which would be the charge, the more of a repulsive or attractive force it has. And the further away you would have the 2 magnets, the more it would decrease the force. Now let's take a look at the periodic table and the trends that the periodic table has with electronegativity. We can see as we go up the column, the electronegativity increases, and as we go from left to right, the electronegativity increases. So when we go left to right, the number of protons and electrons increase. So we know from Coulomb's law that when the magnitude of the point charges increases, the attraction or repulsion will increase. Moving to the second period, this becomes more obvious, where lithium would have 3 protons and 3 electrons, and fluorine would have 7 protons and 7 electrons. So fluorine would have a much greater attractive force than lithium. Going up the column, we can see that electronegativity increases, and this is because the distance decreases as we go up the column because of the shells. Where period 1 would have 1 shell, period 2 would have 2 shells, period 3 would have 3 shells. So these valence electrons at the bottom would be much farther away than the valence electrons at the top. And we know from Coulomb's law that as the distance increases, the force will decrease. Another point to consider: at the bottom of the periodic table, there are several shells in between the electron and the proton. And another way to think of a shell is a cloud, like a misty cloud of a negative charge. And the negative charge of this valence electron has to pierce through each one of these layers that repels the electron, which would make the force decrease. Alright, so let's sum up what we know about electronegativity. We know that electronegativity increases as we go up the column and from the left to the right. We know as we go from the left to the right that the electrons and the protons increase, which would increase the point charge. And we know from the Coulomb equation that as the point charges increase, the attractive or repulsive forces increase. In this case, it would be the attractive force. And we know that as we go up the column, the number of shells decrease, which would decrease the distance between positive proton and the negative electron. We know from the Coulomb equation that as the distance increases, the attractive force will decrease. So in this case, the distance decreases, so when it's closer together, there's more of an attractive force. Along with Coulomb's law, we know that the shells play a role in the attractive forces. Because an electron on the outer valence shell, it has to go through several layers of a cloudy mist or a cloud of electrons or layers of electron. It effectively slightly cancels out the attractive force with each layer that it has to go through, because each layer has a misty cloud of a negative charge, and the negative charge would cancel out the positive charge. Here's a diagram that describes a more visual size difference between the atoms, and we can see that, and this only goes to sodium, but they get bigger as we go down the group. We can see that sodium is a big metal, so it has 3 shells, and it just would not be as electronegative as a non-metal, where it would have an abundant amount of electrons and protons that would increase the total amount of point charges, like fluorine right here. And you can see that there's a lot of electronegativity because they're so small. What that means is the protons are pulling the electrons in towards it because there's so much attraction from all the point charges that don't have to go through all the layers of shells that a metal like sodium would have to go through. Right here is a diagram of bonding where these two dots would be just arbitrary atoms. The dotted line would be the line between repulsion and attraction, which would be at the bottom. And you can see that when atoms get really close together, they start to repel. As they get further apart, they fall into a zone where it's just perfect to bond. And then as they get farther apart, they just don't have enough attraction to pull in the other atom to bond. And what's happening is the positive nucleus or the positive proton of one atom has an attraction to the electrons of the other atom, and it wants to pull it in, and vice versa, where the positive protons on the other atom would have an attraction to the electrons on the other atom. When these would reach the perfect distance, then they wouldn't be too far away and they wouldn't be too close, and they would bond. What happens is when they're very close, like these two atoms up here, what starts to happen is these protons will repel these protons. So the protons from one atom will start to repel the protons from another atom. Before we move on, I wanted to briefly talk about some definitions that you may have heard of that are similar to electronegativity, which is electron affinity and ionization energy. I'm just going to draw a generic atom here to illustrate what this is. Electron affinity describes the ability of an atom to attract an electron And ionization energy is the energy required to remove an electron from an orbit. What these are talking about comes from the framework of a single atom or an individual atom, whereas electronegativity is in the framework of a molecule. So if we had hydrogen chloride, the electronegativity would mostly be on the chloride atom, and it would want to pull most of the electrons towards the chlorine, where the chlorine would have the lion's share of the electrons. When we measure the quantity of an atom's electron affinity, the ability to attract an electron, and an atom's ionization energy, we then have a good idea of how that atom will compete with other atoms. It is only after we consider both of these properties of ionization energy and electron affinity that we can then measure and determine the electronegativity. An example would be fluorine and chlorine, where chlorine has an electron affinity that's actually higher than fluorine, but when we consider the ionization energy, fluorine has a much higher ionization energy than chlorine, and when we add both of these up, we then get the electronegativity, where fluorine would have a higher electronegativity than chlorine. To sum this up, electron affinity is the ability to attract an electron. Ionization energy is the amount of energy that's required to remove an electron. These are properties of a single atom. When we add both of these properties up, we have the electronegativity, and the electronegativity is the ability to compete with other atoms to attract electrons in a molecule. So when an atom can attract electrons to it, and when an atom can hold an electron in its orbit, those add up to good electronegativity, and that atom will compete very well when it comes to competing for electrons with other atoms. Here's a periodic table with the electronegativity of each atom. A general rule to go by is when the electronegativity difference between bonded atoms is less than 0.5, then it's a nonpolar covalent bond. Between 0.5 to 1.9, it's a polar covalent bond, and anything greater is considered to be ionic. So let's look at a few molecules to see what the electronegativity difference is. So if we look up sodium, we can see the electronegativity is 0.9. If we look up hydrogen, we can see the electronegativity is 2.1. So to find the difference, simply subtract 2.1 minus 0.9 equals 1.2, and this falls in the polar covalent category. So this is polar covalent, so this would have a difference of 3.1. So you can see this is clearly ionic because it's greater than 1.9. This would be more polar than this, HCl and OH. So chlorine is 3. We get the difference by subtracting hydrogen. Electronegativity is 2.1. So we have 0.9, and looking at the chart, it looks like it falls within 0.5 to 1.9, so it would be polar covalent. So this is polar covalent. Next we have oxygen, which is 3.5 minus 2.1. We have 1.4. And this looks like it falls in the polar covalent because it's in between 0.5 and 1.9 at 1.4, so it would also be polar covalent. Just an example of a non-polar covalent molecule, if we had diatomic oxygen, so 3.5 minus 3.5 be obviously 0, and that is less than 0.5, so it's nonpolar. Some other examples of a nonpolar covalent bond might be CH4, so carbon be 2.5, and hydrogen is 2.1, so we would have 0.04, and that would be less than 0.5, so it's nonpolar covalent bond. I want to go into these three categories where it's nonpolar, polar, and ionic. I'm just going to put non-P, P, and ionic over here. And we describe this as molecules were either 100% ionic or 100% covalent. And what actually happens is the more we go from the left to the right, it becomes ionic, where 100% ionic would be where an electron transfer goes from one atom to another, and there's an electrostatic charge where it takes an electron completely out of the orbital. And on the other And over here would be the ideal covalent bond where electrons would be perfectly shared equally. The reality is neither one of these extremes really exist, but they're more of a gradient to where nonpolar covalent bond, it has a lot of character where they are shared equally. And as we go over to the ionic part of the spectra, that it would have more ionic character. So there is no binary category where it's either ionic or covalent. It's a spectrum, and it does go back and forth here, where it can have a certain percentage of covalent character and a certain percentage of ionic character. A chemical species in which there is a separation of charge, there is a positive pole on one part of the species and a negative pole on the other part. It's called a dipole. The more we go from nonpolar covalent to ionic, the more of a dipole will develop on a molecule. This is an electron density map that shows a high density of electrons in the red and a low electron density in the blue. So hydrogen would have less electronegativity than chlorine. Chlorine would pull the electrons in closer to it, and it would have a high electron density in that area. The partial positive and partial negative charge on a molecule is denoted by the lowercase Greek letter delta. The octet rule gives us a good way to understand why elements form the ions they do, and it gives us a good way to understand why elements form covalent bonds, but it is not perfect. In this video, I'm going to go on and talk about some of the drawbacks that the octet rule does have. This should give you some context of what Gilbert Lewis was working with. This was a periodic table that was used in 1904. This may have been the arrangement of the periodic table when Gilbert Lewis formed the octet rule, if not very similar to it. When forming ions, the transition metals right here and the inner transition metals right here do not apply to the octet rule. Transition metals oftentimes form more than one ion. An example would be copper, which forms a positive charge of 1 and 2. Boron does not lose 3 electrons to have a charge of positive 3. This would make boron very unstable since it only has 5 electrons. Carbon does not lose 4 electrons to have a positive charge of 4, and it doesn't gain 4 electrons to have a negative charge of 4. For covalent bonds, there are 3 categories where the octet rule does not work. First category is when an element has an odd number of valence electrons. The second category is an incomplete octet. The third category is an expanded octet, or elements that are hypervalent. An example of a covalent bond that does not follow the octet rule that has an odd number of valence electrons would be nitrogen. Nitrogen has 5 valence electrons, and when we look at ammonia, which would be NH3, ammonia fits very well with the octet rule. There's 2 electrons with each bond, so each bond would be 2, 4, 6, and then the 2 lone pairs on the side would be 8. But if we would try to use the octet rule for ammonium, which would be NH4, it would no longer work because each hydrogen would have 1 electron in the valence shell, and the nitrogen has 5 valence electrons in the valence shell. So in order to make a molecule with nitrogen and 4 hydrogen atoms bonded to it, it would end up having 9 valence electrons instead of 8. So one hydrogen would give a single bond and it has 2 electrons on it. Another hydrogen would give a single bond and it has 2 electrons on it. A third hydrogen would have a single bond and it would have 2 electrons on it. And if we put a hydrogen with an electron in the valence shell to this, we would end up having 3 electrons, and this would not work for the octet rule. We deal with this with what is called a coordinating bond. I won't go over it now, but I'll make a video on it to describe how we deal with that scenario. An example of an incomplete octet would be with the element boron. Boron has 3 valence electrons. A common molecule is boron trifluoride. So each fluorine has 7 valence electrons, and they bond to the boron like this. There's 2 bonds and a sigma bond, where fluorine has 8 valence electrons. The second bond has 2 electrons, where it would have a single bond. making the fluorine atom complete an octet of 8 valence electrons. And the third fluorine would have a single bond with 2 valence electrons, and it would have a complete octet. So the boron does not have an octet, and the octet rule would not work with this example. There are some cases where boron will accept a lone pair of electrons and it will complete the octet. I won't go into that right now, but boron with a total of 6 valence electrons is satisfied and stable, so it does not follow the octet rule. So examples of expanded or hypervalent elements would be, or molecules would be phosphorus chloride, where there are 5 bonds to chlorine, and each bond would have 2 electrons, so this would add up to 10. So 2, 4, 6, 8, 10, and this obviously doesn't follow the octet rule because phosphorus has 10 valence electrons. Another common element that's used in compounds is sulfur, and this can have up to 12 valence electrons. Expanded octets often happen in the third period, where an additional orbital is introduced, which is the d orbital. We haven't got into these different types of orbitals. It's what is called as a subshell, and we haven't got into that yet, but we will soon. But that's what's happening, and it introduces another set of orbits. And when that happens, it doesn't follow the octet rule. Another common element that has hypervalency is iodine. An example of hypervalency with iodine would be a compound called IBX. With an introduction to chemistry, oftentimes books and instructors describe this in a very simple and rudimentary way. But I think if this is described in a way that's too simple, I think it's almost too vague to really understand. So what I want to do is start off with a very basic way to draw a molecule, and from there we'll get into more detail. And at the end of this video, you'll have a full understanding on how to draw and represent a molecule with Lewis structures. There are 3 fundamental steps on how to draw Lewis structures to represent a molecule. So when we draw Lewis structures, first we want to determine the number of valence electrons. Next, we want to determine how the atoms are arranged and connect the atoms together with a single bond. And the last thing we do is arrange the remaining electrons so that each atom has a complete octet. Let's do an example with water, which is H2O. If we pull up the periodic table, we have hydrogen and oxygen. And hydrogen has 1 valence electron because it's in the first group. Oxygen has 6 valence electrons because it's in the 6th group. We said hydrogen has 1 valence electron, and there are 2 hydrogens, so that would give us 2 electrons. Oxygen has 6 valence electrons, and there is 1, so that would give us 6 valence electrons. That would leave us a total of 8 valence electrons. So the first step, determine the total number of valence electrons, and we did that by adding them up, so we have 8 valence electrons. So next we determine how the atoms are connected. We know that hydrogen can only be bonded to 1 other atom. It can't be bonded to 2. A molecule like this would not happen. And the other atom that we have is oxygen, and we know that oxygen can form a bond with more than 1 atom. So that eliminates a bond like this. About the only way we can connect these atoms to form a molecule would be where the oxygen is in the center, because we know that hydrogen can only form 1 bond. So step 2 is complete. The last step would be to arrange the remaining electrons so that each atom has a complete outer shell, or a complete octet. We had a total of 8 valence electrons, and when we connected the hydrogens to the oxygen, we used a single bond, so we had 2 single bonds, and that would use up 4 electrons, so that would leave us with 4 electrons. We know that hydrogen has a filled outer shell with a single bond, so both of the hydrogens have a filled outer shell. And oxygen would require 8 valence electrons to complete the outer shell. So we can see that oxygen has 2 bonds, which would bring it to 4 electrons, so it would need 4 additional electrons to fill the outer shell and bring it to a complete octet. So we would put the remaining electrons on oxygen. The third step is complete, and That would leave us with a Lewis structure that looks like this for water. Next, let's draw a methane molecule. The formula for methane is CH4, and the first step is to determine the total number of valence electrons. Pulling up a periodic table, we can find hydrogen, which is in the first group, which would indicate one valence electron, and carbon is in the fourth group, which would indicate 4 valence electrons for each carbon. So we said that carbon had 4 valence electrons, and there was one carbon, giving us 4 valence electrons, and hydrogen had 1 valence electron, and there are 4 hydrogens, which would give us 4 valence electrons. So the total valence electrons would come out to 8 valence electrons. So for step 1, we have 8 valence electrons, so that's complete. In step 2, we determine the connectivity of the atoms and connect the atoms with a single bond. We know that hydrogen can only have a single bond. The only way that would work would be if the carbon atom was in the center and there were 4 hydrogens around the carbon bond, and we connect the hydrogens to the atom with a single bond. At this point, we can count up the number of electrons used to connect the atoms, and we have 2, 4, 6, 8 for 4 bonds. And since we had a total of 8 valence electrons to begin with, this structure is satisfied because in the third step we would arrange the remaining electrons so that each atom would have a complete octet. And we don't need to do that because there are no electrons left, and each atom satisfies a filled outer shell. The hydrogens have 2 valence electrons for all the hydrogens, and the carbon atom has 2 valence electrons with each single bond, so it would have a complete octet as well. So this would be the Lewis structure for methane. Now let's start drawing Lewis structures for double bonds and triple bonds. And for this we can start out with formaldehyde, which has a formula of CH2O. So formaldehyde has a formula of CH2O, and for carbon, it's in the fourth group, so it has 4 valence electrons. And the next one is hydrogen, it's in the first group, so it has 1 valence electron. And oxygen is in the sixth group, so it has 6 valence electrons. So adding up the electrons, carbon has 4 valence electrons, and there is 1 carbon, so that would give us 4 valence electrons. Hydrogen has 1 valence electron, and there are 2 hydrogens, so that gives us 2 valence electrons. Oxygen has 6 valence electrons, and there's 1 oxygen, so that gives us 6 valence electrons for oxygen. So this gives us a total of 12 valence electrons. So for step 1, we have the total number of valence electrons equals 12. So we can move to the second step, which would be to determine the arrangement of the atoms and connect each atom with a single bond. So we have carbon, 2 hydrogens, and an oxygen. One thing that can help determine the arrangement of a molecule is to identify whether or not an atom is a terminal central atom. The hydrogens are always terminal atoms, and this is because the outer shell of the hydrogen can only occupy 2 electrons, so it can only form 1 bond. So hydrogens are always terminal. And central atoms are atoms that can obviously form more than 1 bond, but also have the lowest electronegativity. And when we pull up a chart for electronegativity, we can see oxygen is 3.5 and carbon is 2.5. So carbon would be the lowest electronegativity with 2.5. So carbon is going to be a central atom, and it's going to be bonded to oxygen. And the 2 hydrogen atoms are terminal atoms. They will connect to the carbon. We had a total number of valence electrons of 12, and we have 3 bonds, so that would be 6 valence electrons. So we would have a total of 6 valence electrons remaining. So this completes the second step, and the third step would be to arrange the remaining valence electrons so each atom has an octet. We start this by working on the atoms on the outside of the molecule. We can't put any on the hydrogens because it has a filled valence shell. So we have to come to the oxygen and fill this up so oxygen has a complete octet. The hydrogens have a complete octet. We can see carbon does not have a complete octet. It has 6 valence electrons. We use a lone pair of electrons on the oxygen to make another bond between carbon and oxygen to form a double bond, and we would end up with a molecule like this, where the carbon has a full outer shell of 8 valence electrons, 2, 4, 6, 8. The oxygen has a filled outer shell of 8 valence electrons, 2, 4, 6, 8. And the hydrogens have a filled outer shell of 2 valence electrons. So step 3 is complete, and this meets all the requirements for a Lewis structure. Let's try another pi bond. This time we'll do diatomic nitrogen. So first we determine the number of valence electrons, and we can find at the periodic table nitrogen is in the 5th group, so it has 5 valence electrons. So nitrogen has 5 valence electrons, and there are 2 atoms, 2 nitrogen atoms. So that would give us 10 valence electrons. This one's actually pretty easy, but I wanted to highlight the process on how to form triple bonds. So in the second part, we determine the arrangement of atoms and connect each atom to a single bond. So we have nitrogen and nitrogen connected with a single bond. So we had 10 valence electrons to start off with. We had 1 bond, so we would subtract 2 electrons, and that would give us 8 valence electrons to distribute. The third part is to arrange the remaining electrons so each atom has an octet. We can start on either one of the nitrogens. We have 8 electrons to distribute, so we start on this one. It has 2, 4, 6, 8, and we have 2 left over, so we come over here and we can see that this atom only has 4 electrons, so it would need an additional 4 to reach an octet. We take these 2 lone pairs and turn them into bonds, and we would end up with a triple bond like this. This is verified because each atom has a complete octet. This nitrogen has 2 electrons and 3 bonds with 2 electrons in each bond, so that's 6, and then this one would be 8. So this one completes an octet, and this atom does the same thing. It has 3 bonds with 2 electrons in each bond, so that's 6, and 2 lone pairs right here, so this would complete an octet. So this would satisfy the requirements for a Lewis structure. Another aspect to consider when drawing Lewis structures are molecules that hold a charge. An example of this would be the ammonium ion, which holds a charge of 1. We look at this in the first step where we determine the total number of valence electrons. We said the ammonium ion was NH4+, and nitrogen has 5 valence electrons, and hydrogen has 1 valence electron. So nitrogen has 5 valence electrons, there's 1 nitrogen, so we have 5 valence electrons from nitrogen. Hydrogen has 1 valence electrons, and there are 4 hydrogens, so that's 4 valence electrons from the hydrogens. How we deal with the charge is when a charge is positive on the molecule, we subtract an electron, and when a charge is negative, we add an electron. So this is a positive charge of 1, so we would subtract an electron. The charge of a molecule is completely dependent on the addition or subtraction of electrons. The positive charge does not change. So in this arbitrary model, if we had 4 positive charges and 4 negative charges, and we would subtract a negative charge, the overall charge would be positive 1, because each negative charge would cancel out the positive charge. And if there was a positive charge left with no negative charge to cancel it out, then the positive charge would remain and give us a positive charge of 1. Conversely, if we would add a negative charge, when we cancel out these charges, we would have a negative charge remaining. So we would end up with a negative charge overall. So in the case of the ammonium ion, where it has a positive charge, we subtract a valence electron. And that's how we get a total of 8 valence electrons. So step 1 is complete. Moving on to step 2. So the next step of determining the arrangement of the atoms and connecting them with a single bond is pretty easy. We know that the hydrogen atoms are always terminal and the nitrogen would be the central atom. So we can connect each hydrogen to the nitrogen with a single bond. When we do this, we use up all the valence electrons and the bonds. We have 2, 4, 6, 8. So the structure is complete. And to account for the positive charge, put brackets around the structure and put a positive charge on the upper right hand corner. So at this point, we don't have to go on to step 3 because the requirements are satisfied for the Lewis structure. So in the beginning, we started with a very rough outline of how to draw a Lewis structure, and from there we went on to different components that can be added when drawing a Lewis structure. Now we can collect everything we know about drawing a Lewis structure and develop a strategy from start to finish with everything we've went over. Number 1, determine the total number of valence electrons that must appear in the structure. Number 2, subtract electrons with every positive charge and add electrons with every negative charge. Number 3, determine what atoms are central atoms and what atoms are terminal atoms. All hydrogen atoms are terminal atoms. With central atoms, we usually take the atoms with the lowest electronegativity. Number 4, we write a plausible structure. We join the atoms in a skeletal structure by a single covalent bond. Number 5, for each bond in the skeletal structure, subtract 2 valence electrons from a total number of valence electrons. Number 6, with the valence electrons remaining, first complete the octet of the terminal atoms. Then, to the extent possible, complete the octet of the central atoms. Number 7, if one or more central atoms are left with the incomplete octet, move lone pair electrons from one or more of the terminal atoms to form multiple covalent bonds to the central atoms. The 8th and most important step is to verify. Make sure the number of valence electrons in the final molecule are the same as the number of total valence electrons determined in step 1. After that, make sure that each atom has a filled outer shell of 8 valence electrons, with the exceptions of hydrogen, as hydrogen only requires 2 electrons to complete the outer shell. Let's go over a few structures using this new checklist to write Lewis structures. Let's first try ethylene, and it has a formula of C2H4. First, we have to determine the total number of valence electrons. Pulling up a periodic table, we said the formula was C2H4. So carbon is right here, the 4th group, which would indicate it has 4 valence electrons, and hydrogen is right here, first group indicating it's got 1 valence electron. So starting off with carbon, it has 4 valence electrons, and it has 2 atoms, giving us 8 valence electrons. Hydrogen has 1 valence electron. It has 4 hydrogens, so that would give us 4 valence electrons, giving us a total of 12 valence electrons. So step 1 is complete with 12 valence electrons. Moving on to step 2, there is no charge, so we can skip step 2. Step 3, we determine what atoms are central atoms and what atoms are terminal atoms. We know that the hydrogen atoms are always terminal atoms, so the carbon atoms must be central atoms. So step 3 is complete. So in step 4, we write a plausible skeletal structure to join the atoms by a single covalent bond, which is represented by a single dash. The hydrogen atoms are the terminal atoms, so we start with the central atoms, and there's only 2, so we write the 2 carbon atoms with a single bond between them, and there are 4 hydrogen atoms, so we join those to the carbon with a single bond, and we have this structure. Step 4 is complete. In step 5, for each bond of the skeletal structure, we subtract 2 from the total number of valence electrons in step 1. So we determined that there were 12 valence electrons in the molecule. There are 1, 2, 3, 4, 5 bonds in the skeletal structure, and each bond has 2 valence electrons. We subtract that from the total number of valence electrons, which would be 12. So 12 minus 10 is 2. So step 5 is complete. Moving on to step 6, with the valence electrons remaining, first complete the octet of the terminal atoms, then to the extent possible complete the octet of the central atoms. And at most, hydrogens can only form 1 bond, so these outer shells are complete for all the hydrogens. And the only atoms or elements at this point that are incomplete would be the carbon atoms. And we have 2 valence electrons, so we place those on one of the carbon atoms. Remembering these have to be placed on the atom in pairs, so we can only put it on one carbon atom. So step 6 is complete. Looking at step 7, if one or more central atoms are left incomplete in the octet, move the lone pair electrons from one or more terminal atoms to form multiple covalent bonds to the central atom. Since the terminal atoms, hydrogen, are complete, we start with the pair of electrons on the central atom, but we do the same thing. We can see this carbon has a complete octet. It has 2 lone pairs and 3 bonding pair electrons, but this carbon only has 3 bonding electrons. So we move the lone pairs from this carbon to form a double bond, which then gives us a structure that looks like this. A feature that's held in the bonding electrons is that whatever they are bonding to counts towards the completion of an octet in both atoms. So now we have a double bond, and these electrons will count towards the completion of the octet in this carbon and in this carbon. When before we had a lone pair of electrons, and the alone pair of electrons will only count towards the completion of the octet in the atom that they're attached to. So when we move the lone pair electrons from lone pair electrons on this atom to a bond between both of the atoms, the electrons can then be counted towards the octet of both atoms. So step 7 is complete, and we now have a structure of ethylene that looks like this. And the last and most important step is to verify what is required for a Lewis structure. So the first part is to make sure that the number of valence electrons in the final molecule are the same as the number of total valence electrons in the first step, which would be right here, and we had 12 valence electrons. And the next part is to make sure each atom has a filled outer shell of 8 valence electrons, the exceptions of hydrogen, as hydrogen only requires 2 electrons for a complete outer shell. These guidelines, let's go ahead and quickly evaluate this molecule. So we determined the first step that there are 12 valence electrons right here, and in the molecule there are 2, 4, 6, 8, 10, 12, so this part of the guidelines are met. In the second part, all the hydrogens have a filled outer shell of 2 electrons with a single bond right here, and there's 4, so that part is met. And each carbon has 8 valence electrons from each bond. This carbon has 2, 4, 6, 8. This carbon has 8 valence electrons, and this carbon has 2, 4, 6, 8. So this carbon has met the requirements of 8 valence electrons. So the second part is met, and finally you can say the requirements for a proper Lewis structure has been met. In this video, I want to go over a few tips and tricks that you can use to determine how atoms are connected when drawing a Lewis structure. The first tip would be to use the single atom in the formula as the central atom. When molecules have a formula that look like either one of these 2 generic formulas, where one atom is a single atom and another atom is a multiple of atoms, like B would be a single atom here and A would be a single atom in this formula, usually those can be used as the central atoms. An example that uses this formula or this pattern of formula would be water, where it has H2O. The hydrogen, there would be more than one hydrogen, and the oxygen is the single atom. So the oxygen is the central atom. And from there, we can usually connect the atoms together pretty quickly. An atom that uses this format that looks similar to this would be methane, where carbon is the central atom and there's multiple hydrogen atoms. So we know right away the carbon will be in the central atom, and from there we can connect the rest of the atoms pretty quickly. When we see a formula like this, we'll know right away that the single atom goes to the center. An example would be the ammonium ion. We know right away that there's a single nitrogen, so that's going to go in the center. And we know that the hydrogens surround the nitrogen. We can usually connect those pretty quick after we find out which atom is the central atom. Another example, SO2. Sulfur is a single atom, so we know right away that that's going to be the central atom. And from there, we can figure out pretty quickly where the rest of the atoms go. The second tip would be to use the honk method. I think it's so simple that it's just really easy to remember, and it works. So we know that hydrogen can only form 1 bond. Oxygen usually forms 2 bonds. Nitrogen usually forms 3 bonds. And carbon usually forms 4 bonds. Whenever you have a formula It'll give you a general guideline to put the molecule together. I'm just going to do formaldehyde. So CH2O, so right away we know that carbon is going to have 4 bonds, hydrogen is going to have 1 bond, and oxygen is going to have 2 bonds. And if we look at the actual Lewis structure of formaldehyde, I'm not going to go through the whole thing, but I just want to point out how really useful this little tip works. So this is a Lewis structure of formaldehyde, and we can see that carbon has 4 bonds, 1, 2, 3, 4. We can see that the hydrogens have 1 bond for each hydrogen. This hydrogen has 1 bond, this hydrogen has 1 bond. So that checks out. And the oxygen has 2 bonds. And in this case, it's a double bond, but this checks out too. So knowing this, we can write how many bonds each atom has and almost snap them together. So oxygen has 2 bonds and hydrogen has 1 bond. So it's going to be like this. Carbon has 4 bonds, hydrogen has 1 bond. So molecule is going to look like this. And nitrogen has 3 bonds, so we know that it's going to look something like this. Actually looks like this. But it's a good guide to use when you come up to the step in the Lewis structure where you have to connect the molecules. A third tip would be to determine what atoms are central atoms and what atoms are terminal atoms. Hydrogen atoms are always terminal atoms because they can only form 1 bond. And the central atom is usually the atom with the lowest electronegativity. We went over this in a previous video, but I did want to add this to part of the tips to use when you're connecting atoms for a Lewis structure. So using formaldehyde again, carbon has, I think carbon has an electronegativity of 2.5, and oxygen has something like 3. So the lowest electronegativity would obviously be, so that's going to be the central atom. We know that the hydrogens are always terminal atoms, so we can put those here. And the only atom that's left is the oxygen. They're obviously not going to go on the hydrogens, so we can connect that then to the carbon atom, and that would be the skeleton of the Lewis structure. Just to finish this up, the Lewis structure would look like this. And the fourth tip is when molecules are made up of carbon and hydrogen, carbon is usually always the central atom and hydrogen is always the terminal atom. This usually takes place in organic chemistry. An example would be C2H4 ethylene. The carbon atoms are the central atoms, so we have something like this, and then the hydrogens would come off the carbons, and they are the terminal atoms. But usually all atoms that are made up of carbon and hydrogen, the carbon is usually always the central atom and hydrogen is always the terminal atom. So in summary, the first tip, use the single atom in a formula as the central atom. The second tip is the HONC method. HONC, H-O-N-C equals 1, 2, 3, 4. And the third tip is to determine what atoms are central and terminal atoms. Hydrogen is always a terminal atom, and the central atom is usually the lowest in electronegativity. And the fourth tip is when molecules are made up of carbon and hydrogen, carbon is usually always the central atom, and hydrogen is always the terminal atom. In this video, I want to talk about formal charge. I'll go over what it is, how it works, and what we can use it for. First, we need to know what a formal charge is. A formal charge is a hypothetical charge on an atom in a molecule or a polyatomic ion. A formal charge must not be confused with the charge of a molecule, a charge due to the surplus or the lack thereof electrons in the molecule. We looked at molecules with charges and drew them with brackets around the molecule with the charge on the upper right-hand corner. The charges on the molecule gave no indication where the charge was in the molecule. A formal charge gives us a more specific location of the charge, revealing which atom holds the charge within the brackets of the molecule. A formal charge can be abbreviated by Fc or denoted as Q star. The formal charge is represented by a charged value with a circle around it and placed by the atom it represents within the molecule. So this charge represents the entire molecule, and this charge represents the hypothetical charge on the nitrogen atom. How does it work? When we use a strategy to draw Lewis structures, once we determine the number of valence electrons in the molecule, there is really no way to keep track of them after we determine how many there are. Then we arbitrarily go back and assign these valence electrons to atoms as if we know where they came from. A formal charge gives us better bookkeeping skills to keep track of the valence electrons in the molecule, so there is less ambiguity. This is done by using a more detailed and accountable method to make sure charges in the atom make sense. With this extra set of guidelines to follow, we can make sure the valence electrons are distributed accurately and correctly throughout the molecule. This added insight gives us more confidence the structure is correct. A formal charge is a hypothetical charge on an atom in a molecule or polyatomic ion. This is hypothetical because it assumes bonding electrons are shared equally between the atoms involved, which is an idealized situation. In reality, electrons are usually not shared equally. A formal charge does not consider polarization or polar covalent bonds that are brought about by electronegativity. This over-exaggerates the covalent character of bonds equally sharing electrons. So why is the formal charge so important and what do we use it for? We kind of went over this when we described how the formal charge worked. To get straight to the point of what a formal charge is used for, a formal charge can help us determine the correct distribution of electrons throughout the molecule and write a correct Lewis structure in most cases. We won't get into it in this video, but a formal charge can also help to write the correct resonance structure, which is a very important concept in chemistry. In a previous video, we were drawing a Lewis structure for carbon dioxide, and we came up to a point where we were going to distribute the electrons so we could get carbon to have a filled outer shell of 8 valence electrons. And the first step, we took the lone pairs on the oxygen on the right and distributed those out to a bond between the oxygen and the carbon. And we got to this point right here. And at this point, we could have either went to the oxygen on the left and distributed those out to a bond between the oxygen and the carbon, or we could have went to the oxygen on the right and distributed a lone pair of electrons to an additional bond between the carbon and the oxygen, which would give it a triple bond. And there's nothing that would indicate which molecule would be correct from the rules given to us on how to draw a correct Lewis structure. Both of these molecules would pass the verification test. They both have the same amount of electrons as they would have had in step 1. And all the atoms in the molecule would have a filled outer shell of 8 valence electrons. So in situations like this, a formal charge can be applied, and it'll become very clear on which one is the correct Lewis structure. When we calculate the formal charge, we need to find out 2 types of valence electrons: the valence electrons in a free atom, and the valence electrons assigned in the Lewis structure. Once we determine those valence electrons, we subtract the valence electrons from the Lewis structure from the valence electrons in the free atom. Valence electrons of a free atom simply means it's an uncombined atom. It's not bonded to anything else. And we find the valence electrons the same way we do when we write a Lewis structure. We just pull up a periodic table and find what group the atom falls in, and that will give us the valence electrons of that atom, or a free atom. So if we had carbon, it would be in group 4A, so it would have 4 valence electrons. Nitrogen would be in 5A, so it would have 5 valence electrons. Oxygen would be in 6A, so it would have 6 valence electrons, and so on. So the valence electrons of a free atom simply means the atom by itself that is not combined with another atom. We can find that by pulling up a periodic table and seeing what group it's in. The other type of valence electrons we need to know are the valence electrons that are assigned to the atom in the Lewis structure. There are 2 categories of valence electrons in a Lewis structure: lone pair electrons and bond pair electrons. The lone pair of electrons are lone pairs of electrons belonging entirely to the atom that they're attached to, and the bond pair of electrons are electrons in the bond, and they're divided equally between the bonded atoms. When we count up the valence electrons assigned in the Lewis structure, this is equal to the number of lone pair of electrons plus half of the bond pair electrons. So mathematically, we could write it out like this. Let's go ahead and start adding up some valence electrons that are assigned to atoms in this molecule. So let's start with oxygen. And starting out with the lone pair of electrons, we can see there's 2 lone pair of electrons, so that would give us a total of 4 valence electrons. There are 2 bonds that are bonded to oxygen, and each bond has 2 valence electrons in it, so that would give us a total of 4 valence electrons. And here we say that we get half of the bond pair electrons. We divide that by 2, and that would give us 2. So we could put 2 right here for half of the bond pair electrons, which would give us a total of 6 when we add them together. So for oxygen, there would be 6 valence electrons assigned to oxygen. Let's look at carbon. Carbon has 4 bonds, and each bond has 2 valence electrons in it. So that would be 8 valence electrons, and we would only get half of those. So that would give us 4 valence electrons. There are no lone pair electrons, so carbon would have 4 valence electrons. Looking at hydrogen, it has no lone pair electrons, and it has 1 bond, and each bond has 2 valence electrons, and we divide that by 2, which would give us 1, so each hydrogen has 1 valence electron. We know what valence electrons are in a free atom, and we know how to get them. And we know what valence electrons are that are assigned to a Lewis structure, and we know how to get them. We know how to calculate the formal charge, which is done by subtracting the valence electrons on the Lewis structure from the valence electrons of a free atom. We use these abbreviations to describe what each valence electron was, and if we plug those into the formula right here, we can get this final formula, which would describe how to get the formal charge. So we take this description and simply plug it into this part of the formula, and we take this description and plug it into this part of the formula, and we arrive at a formula that looks like this, which just describes the formula in more detail. We abbreviated the valence electrons in a free atom. To be more descriptive, we have the number of valence electrons in a free atom. So with the 2 types of valence electrons, one from the free atom and then one that's on the Lewis structure, if we distribute out this negative sign and take away the parentheses, we have a more simplified formula, so we can just plug the values in and subtract. And subtraction is a little less cumbersome than this formula right here. So with our final equation, we can go ahead and evaluate a molecule. The order of the equation is we have the number of valence electrons in a free atom minus the number of lone pair of electrons minus half of the bond pair electrons. First up is hydrogen, the number of valence electrons in a free atom. We can find that on the periodic table. Hydrogen's in the first column. We know it has 1 valence electron. And looking at the molecule, we know that it has 0 lone pairs, and it has one bond. So each bond has 2 valence electrons, and we get half of that, so we would have 1 bond. So 1 minus 0 minus 1 give us 0. And looking at the other hydrogen, which is the same, so we would have the same formal charge with the other hydrogen. Looking at carbon, the number of valence electrons in a free atom would be 4. Carbon is in the 4th group on the periodic table. Looking at the molecule, we can see that carbon has no lone pairs, so we have 0 for that. And it has 4 bonds, and each bond has 2 valence electrons. So 4 times 2 is 8, and we get half of the bonding electrons, so that would give us 4. So 4 minus 0 minus 4 would give us 0. Next up is oxygen. We can find the valence electrons of a free atom by going to the periodic table, and oxygen is in group 6, so it has 6 valence electrons. And looking at the molecule, it has 2 lone pairs, and each lone pair has 2 valence electrons, so that would be a total of 4 valence electrons. Oxygen has 2 bonds, and there are 2 electrons in each bond, so that would be a total of 4 valence electrons for the bonding electrons, and we get half of those, so that would give us 2 valence electrons for the bonding electrons. So we have 6 minus 4 minus 2 would leave us a formal charge of 0. So this is a neutral molecule, and everything checks out because there's no charge or brackets around the molecule. Here are some guidelines to follow when we're writing a formal charge on a Lewis structure. Number 1, the sum of the formal charge in a Lewis structure must equal 0 in a neutral molecule and must equal the magnitude of the charge in a polyatomic ion. Number 2, when formal charges are required, they should be as small as possible. Number 3, negative formal charges usually appear on the most electronegative atoms, and positive formal charges on the least electronegative atoms. Number 4, structures having formal charges of the same sign on adjacent atoms are unlikely. Let's go ahead and review the molecule that we just evaluated with these guidelines. We determined that there is a formal charge of 0 on every atom, and if there's a formal charge of 0, we don't put anything on the atom. Looking at the first guideline, it says the sum of the formal charge in the Lewis structure must be 0 for a neutral molecule and must equal the magnitude of the charge in polyatomic ions. So this checks out. All the formal charges are 0, and it's a neutral molecule. The next three rules really don't apply. Where formal charges are required, they should be as small as possible, and they didn't have formal charges. The third rule says that negative formal charges usually appear on the most electronegative atom, and positive formal charges usually appear on the least electronegative atom, so this doesn't apply. And the last one says structures having formal charges of the same sign on adjacent atoms are unlikely. Doesn't apply. So with the rules that do apply, they check out. Previously, we used this slide as an example of how a formal charge could help us decide the correct Lewis structure. So I want to take both of these molecules, this molecule and this molecule, and put formal charges on them and see what we got to help us determine what the correct molecule is. We have an oxygen, 3 sets of lone pair electrons, and 1 bond. Next up is the carbon, and we have 4 bonds on the carbon. In the last oxygen, we have 3 bonds and a set of lone pair electrons. So starting off, we can determine the number of valence electrons in the free atom, and we can do that by going to periodic table. Oxygen is in group 6, so it would have 6 valence electrons. It has 3 sets of lone pair of electrons, and there's 2 valence electrons in each lone pair of electrons, so that would be 6 valence electrons. It has 1 bond, and there's 2 valence electrons in 1 bond, and half of that would be 1, so we have 1. So 6 minus 1 is negative 1. So for this oxygen, we can put a negative formal charge on it. We put a negative sign with a circle around it. For the next atom, we have carbon. So the number of valence electrons in the free atom can be found on the periodic table. And it's in group 4, so the free atom has 4 valence electrons. Next, we have the number of lone pair electrons, and it has no lone pair electrons. And it has 4 bonds, and each bond has 2 valence electrons, so that would be a total of 8 valence electrons. And we take half of those, so that would leave us with 4 valence electrons. And 4 minus 0 minus 4 equals 0, so we don't have to put anything on the carbon atom. In the last oxygen, we can find the valence electrons, the number of valence electrons in the free atom by going to the periodic table. Oxygen's in group 6, so it has 6 valence electrons. It has 1 set of lone pair of electrons, so it has 2 valence electrons for that. And it has 3 bonds. Each bond has 2 valence electrons, so that would be a total of 6 valence electrons. And we take half of those for the oxygen, so that would be 3 valence electrons. So 6 minus 2 minus 3 equals positive 1. And we can put this formal charge on this atom by putting the sign on it with a circle around it. If it's 1, then we can just put the sign on there. If it was more than 1, we would put magnitude of the charge with a circle around it in the sign. Okay, let's go ahead and review this molecule with these 4 guidelines. We said there is a negative formal charge on this oxygen. The carbon was neutral, and there was a positive charge on this oxygen. So looking at the first rule, the sum of the formal charge in the Lewis structure must equal 0 for a neutral molecule. And this is a neutral molecule, so this checks out. For the second guideline where it says where formal charges are required, they should be as small as possible. For this guideline, I want to wait until we have all the structures built up so we can compare them and better determine which one has the lowest formal charge. The negative formal charges usually appear on the most electronegative atoms and positive formal charges on the least electronegative atoms. And the oxygens are the most electronegative, so that checks out for this oxygen. But this oxygen has a positive formal charge, and that doesn't make sense because the carbon would be the least electronegative. So this fails. All right, let's move on to the fourth and last guideline. It says structures having formal charges of the same sign on adjacent atoms are unlikely. So on the left, we have an oxygen that's negative, and on the right, we have an oxygen that's positive. In the center here, where the carbon is, this is a neutral carbon.
So this would make it impossible for two atoms of the same formal charge to be next to each other. So this checks out.
When we review this molecule with a formal charge of -1 on the left oxygen would check out, but a formal charge on the right oxygen where it has a positive formal charge does not check out. This does not make any sense. The other option we had was a molecule that looked like this. Let's go ahead and put this up on the chart and see what we get. Going left to right, we had an oxygen with two sets of lone pair electrons and two bonds. Next up, we had carbon with 4 bonds. And the last one, we had an oxygen with two sets of lone pair electrons and 2 bonds. I'm going to go through this pretty quick since we already did one previously. So the number of valence electrons in a free atom is in group 6, and that's 6 valence electrons. There's two sets of lone pair electrons, so there's 2 in each one, so that would give us 4. And there's 2 bonds, and there's 2 valence electrons in each bond, and we get half of those. So that would give us 2. So 6 minus 4 minus 2 would be 0. With carbon, carbon is in the 4th group, which would give us 4 valence electrons for a free atom. There are no lone pair electrons, and there are 4 bond pair electrons, which would give us 8 valence electrons total, and we get half of those, so that would be valence electrons. And 4 minus 0 minus 4 would be 0. And this oxygen is essentially the same as the oxygen on the top row, so I'm going to put 0 there, and we have 0 formal charges on all 3 atoms. We determined that this had a formal charge of 0 and that it was a neutral atom. So looking at step 1, the sum of the formal charge in the Lewis structure must equal 0 in a neutral molecule. The second guideline is where formal charges are required, they should be as small as possible. The third guideline is negative formal charges are usually on the most electronegative atom, and positive formal charges are on the least electronegative atom. Since we don't have any formal charges, this guideline would really not apply. And the last guideline is structures having formal charges of the same sign on adjacent atoms are unlikely, and this doesn't apply because we don't have any formal charges. It's a neutral molecule. So this does not fail any of the tests or guidelines. This would be the correct Lewis structure for carbon dioxide.
I do want to circle around, come back to the first structure we had, and look at the second guideline where it says where formal charges are required, they should be as small as possible. And I wanted to wait until we had both structures so we can compare them, because it's really the only way you can apply the second guideline. It's pretty obvious once you have all the structures lined up next to each other. This structure has a formal charge of 1 on each side, right here and right here. The last structure we had was this structure, and it has no formal charges. So obviously that's the molecule that has the smallest formal charge. In summary, we knew right away the molecule with the formal charges on it would be rejected. This is because there was a positive formal charge on the oxygen with high electronegativity. In addition to the mismatched formal charges, once we compare the two molecules together, it would become obvious that one of the molecules would have no formal charge, and that would be the correct molecule.
In a previous video, we used this equation to calculate formal charge. I want to go to this part of the equation, and it says we only use half of the bond pair electrons when calculating a formal charge. So this part of the equation best describes what we're actually doing. The drawback is the process becomes very redundant, where if there's one bond, we would have 2 valence electrons, and we would divide that by 2 because we only use half, which would equal 1 valence electron. So what we could do is skip that part and just simply say 1 bond equals 1 valence electron, and we get an equation that looks like this. So let's run it and calculate a formal charge. Hydrogen has 1 valence electron, it has no lone pair electrons, and it has 1 bond. So we come up with a formal charge of 0. Nitrogen has 5 valence electrons, it has no lone pair electrons, and it has 4 bonds. So we have a charge of positive 1, and we can put that next to the nitrogen, the circle around it. The nitrogen has a positive formal charge.
As we develop a better understanding of covalent bonding, we will see that for some molecules and ions, there is no single Lewis structure that can be drawn to represent or fully describe the molecule that we are trying to draw. This brings us to our next tool we have to draw molecules, which is called a resonance structure. So what is a resonant structure in organic chemistry? A resonant form is another way to draw a Lewis dot structure for a given compound. Equivalent Lewis structures are called resonant forms. They are used when there is more than one way to place double bonds or lone pairs on an atom. Let's take a look at the carbonate ion, which is CO3, the -2 charge. So drawing the structure, we get something that looks like this. We put the -2 charge out here. Let's evaluate this molecule and see what we got. So in the top oxygen, we have 3 sets of lone pair of electrons, which would give us 6 valence electrons, and we have a bond pair, which would give us 8 valence electrons. So this would satisfy the octet rule. Put a check right there. So looking at the lower right oxygen, we have a bond pair, and we have 3 sets of lone pair of electrons, so we have 8 valence electrons on this atom, and this satisfies the octet rule, so we can put a check there. Looking at the carbon, we have 2 single bonds, 2 different single bonds, and we have a double bond. Each bond has 2 valence electrons, so that would bring us up to 8 valence electrons, and that would satisfy the octet rule. So carbon can get a check. Looking at the lower left oxygen, we have an oxygen with a double bond and 2 lone pair of electrons. So that gives us 8 valence electrons, and this satisfies the octet rule, so we can put a check on that. So this molecule is good and sound. It satisfies the octet rule. But if we take a closer look at it, we can see that we can put this double bond that's on the lower left oxygen on any of the oxygens, and it would check out just fine. So then the question becomes, how would we make a structure that would represent that, where we could show that there's a double bond on each one of the oxygens? We could also have a structure that looked like this, and we could just as easy do the same thing with right here. This is where resonance structure comes in. We write each of the possible structures. So we have a double bond here, we have a double bond here, and we have a double bond here. And in between each structure, we write a double-headed arrow. And what this is saying is these 3 structures are a hybrid representation of what the true molecule would look like. So what's that mean? That means that it has characteristics of this structure, it has characteristics of this structure, and it has characteristics of this structure. So it means there's a little bit of a double bond character on each oxygen. In this video, I want to go over bond angles and covalent molecules. I'll go over what they are, how they can be predicted, why they're important, and how they can be used chemically. First, let's look at what bond angles are in a covalent molecule. Bond angles in a covalent molecule are exactly what they sound like they would be. They're the angles of the bonds that are in the molecule. There are 3 main types. There's a linear angle, there's a trigonal planar, and there's an angle that is tetrahedral. This is a hydrocarbon, it's methane, and it has a tetrahedral geometric shape. So with this shape, if we take any of the hydrogens on the outside and measure from one to the other, it will be 109.5 degrees. If we took this hydrogen and measured the angle between this hydrogen and this hydrogen, it would be 109.5 degrees. We could also take this hydrogen and measure the angle, and it would be 109.5 degrees. And we could do that with any of the hydrogens with the tetrahedral geometric geometry. In a previous video, we did resonance structures, and we used the carbonate ion, and that molecule had the trigonal planar shape. In between any of these oxygens, whether it's between this oxygen and this oxygen, or this oxygen and this oxygen, should have an angle of 120 degrees or close to it. If there's a double bond, one atom may skew a couple degrees, but generally the trigonal planar is 120 degrees. Looking at a molecule that's 180 degrees, we have carbon dioxide. This is a molecule that we also did in a previous video, which is also known as a linear molecule. So now the question becomes, how do we predict the bond angles in covalent molecules? We can predict bond angles in molecules by using the valence shell electron pair repulsion model. Before we get into that, let's take a look at the structure of an atom. An atom has a center nucleus, which has a positive proton and a neutrally charged neutron that's in the center. And in the outside of the atom, we have the electrons, which are negatively charged. So if we have 2 atoms, atom A and atom B. The electrons on the outside of the atom that are negatively charged, the valence electrons, the outermost electrons on the atom, are going to repel the outermost electrons on atom B because they both have a negative charge. So now we know that the valence electrons from one atom will repel the valence electrons from another atom, and they'll want to get as far away from each other as they can possibly get. And through that reasoning, we can predict what shape the molecule will take on. Let's use the hydrocarbon methane as an example. Methane has a formula of CH4. We can put carbon in the center, and the hydrogens would be around the carbon. In order for the valence electrons for the hydrogens to be as far away from each other as they possibly can, the methane molecule would have to take on the shape of a tetrahedron. So this hydrogen is coming out of the screen, this hydrogen is going into the screen, and these two hydrogens be on the plane of the computer screen. Let's take a look at the carbonate ion and carbon dioxide. So in order for the oxygens on the carbonate ion to be as far away as they possibly can be, they have to take on a trigonal planar shape, and the bonds would be 120 degrees apart. We determine that carbon dioxide has a Lewis structure like this. You can see that the bond angle is 180 degrees. Once we determine the bond angle and the shape of a molecule, we can then determine some of the properties that that molecule may take on. Let's take a look at water, carbon dioxide, and methane. As we can see, carbon dioxide has a linear shape of 180 degrees. Methane has a tetrahedral shape of 109.5 degrees. Water is a bit different. It has a bond angle of 104.5 degrees, and that's because these two lone pair of electrons on the oxygen atom repel the electrons on the hydrogen atoms. This makes the water take on more of a tetrahedron shape. This slight difference a water molecule has of 104.5 degrees gives it some unique properties that most other molecules don't have. One of these properties is when water goes from a liquid to a solid, the volume actually increases, where most other molecules, the volume will decrease. And the increase in volume makes the solid form of water less dense than the liquid form of water, which is why ice floats on water. This unique angle that water has of 104.5 degrees is very important. If water took more of a tetrahedron shape, where the bond angles were 109.5 degrees apart, or if water had a more linear shape where the bond angles are 180 degrees apart, water would be very different than what we are used to. For example, if water was more linear, it may be a gas at room temperature instead of a liquid. Now let's take a look at how the shapes of molecules can be used in chemistry after they're determined. The shape of a molecule and the bond angles that it has can have a very big influence on the stability of the molecule and the reactivity it has with other molecules.